Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR NET, GATE, NTA exam, PhD exam, SET exam, Jest, Tifr, IIT-Jam exam and other exams related to physical science. So so before starting the class, I would request the people who haven't subscribed my channel yet, please subscribe my channel and watch my free live classes, and they are going to help you to crack the exams related to physical science. Okay, so we are solving CSIR NET Physics PYQ June 2019. Okay, so it is the sixth part of the series of Physics PYQ of CSIR NET of June 2019. Okay, so this is the sixth part. So I'm going to start with question now. Okay, question number one is the Hamiltonian of a classical non-linear non-linear one-dimensional oscillator is h equal to 1 by 2 m p square, that is p square upon 2m, plus lambda x to the power 4. Very good question, guys. Where lambda greater equal to 0 is a constant the specific heat of a collection of collection of a collection of a collection of n independent such such oscillators is. Okay, options are: option number A is 3 3nk 3nk upon 2. K is Boltzmann constant, guys. Okay, and option B is 3nk by 4. 3nk by 4, it is kb, that is Boltzmann constant. I'm just writing k. Okay, option C is nk. For convenience, I'm writing k. Okay, and option D is nk by 2. nk by 2. Okay, so this is the question. Question is a Hamiltonian of a classical non-linear one-dimensional oscillator. Okay, so the Hamiltonian of non-linear classical one-dimensional oscillator is given, okay, and lambda which is greater than 0, which is constant. Specific heat we need to find out of a collection of n independent such oscillators, okay. This we need to find out, okay. So I will solve it. Since h is given, that is p square upon 2m, p square upon 2m plus lambda x to the power 4 plus lambda x to the power 4 and lambda greater equal to 0, where lambda greater equal to, okay. So this is the Hamiltonian which is given, okay. Now we will find the total energy, okay, total energy, that is average total energy of the system, or we can write average of h or total energy, and this we know, uh, p square upon 2m, average of p square upon 2m, okay, plus average of, that is potential energy, right? This we know, okay. And for non-linear harmonic oscillator, the kinetic energy is, okay, for non-linear harmonic oscillator, okay, the that is classical harmonic oscillator, okay, the kinetic energy we know, this energy is 1 upon 2 kT. K is the Boltzmann constant, okay, plus V, which we are going to find out. So V is going to be, we have been given, right, that is lambda x to the power 4, okay. So this is going to be, so we'll find the uh, average the average kinetic energy for V, that is this one, right? This is kinetic energy, and this is potential energy for lambda x to the power 4, and that we know how to find out, right? So it is going to be minus infinity to plus infinity, uh, x to the lambda x to the power 4, right, e to the power minus beta e. So we know how to find it, right? I'll write it first for you, like kinetic energy, the energy, that is, for example, suppose energy V average, that we can find out like this: energy, that is integration minus infinity to plus infinity, okay, energy, that is V e to the power minus beta V, okay, upon integration minus infinity to plus infinity e to the power minus beta e, that is beta V, right? This we know. So by this formula we can find the average value of the average energy of the system, right? So for this we'll find out, okay, this we know, guys, okay. If its energy is E, then we can write beta E. So similarly for here we'll do, that is integration minus infinity, and this value we know, that is 1 upon kT, okay. So no need to calculate it, and this is going to be minus infinity to plus infinity, okay, and then that is V is given lambda x to the power 4 e to the power minus beta e, right, e to the power minus beta, value of e is lambda x to the power 4, okay, and then dv, or sorry, dx, right, because it is in one dimension. So this is dx, one dimension, right? Dx upon integration minus infinity to plus infinity e to the power minus beta lambda x to the power 4, that is beta e dx, right? This we need to, this integration we need to find out. We will find out it we can find out it. It's an easy integration. I'll tell you the trick, okay. I'll tell you the procedure and formula for it, okay, right? So this will remain as it is, that is 1 upon 2 kT, okay. Well, I'm just checking it. Okay, and then this is going to be, so we'll convert it because these are even function, right? So we'll change the limit. So limit is going to be, we'll make it like 2 into 0 to infinity. Okay, lambda will take outside, and this is going to be x to the power 4 e to the power minus beta lambda x to the power 4 dx upon, and this is going to be again we'll change, we'll take the limit, right? So it is going to be 2 0 to infinity, right? So we have taken 2 outside and 0 to infinity, and then this is going to be e to the power minus beta lambda uh, x to the power 4 dx. Okay, well, next, total average energy is going to be, this is going to be 1 upon 2 kT. Let me just check the voice, guys. Am I audible or not? Because many times I have faced this issue. That's why I'm just checking. Minus, yeah, I am audible. Okay. So now this integration is going to be, so now we can we can easily calculate this integration, right? This integration. I'll tell you how to calculate it. Okay. So I'll write a formula first, okay, and then I will calculate it. So there's a formula. The formula is integration 0 to infinity, okay, x to the power 4, or x to the power n we can write in general, x to the power n, x to the power n, e to the power minus alpha x to the power n dx. Okay, if we have to solve this integration, right, this is going to be gamma n plus 1 by n, okay, upon alpha, upon n into alpha to the power n plus 1 upon n. Okay, this is the formula. Another formula is integration 0 to infinity. You need to note down and memorize it, guys. Very important formula. And this is e to the power minus alpha x to the power n. Okay, if we have like this dx, only this. In that case, it is going to be gamma n plus 1 by n upon, this is going to be alpha to the power 1 by n. Okay, gamma n plus 1 upon alpha to the power n minus 1 upon n. Okay, so these two are a very important formula which we are going to use here. Okay, here n is 2, sorry, n is 4. Okay, and here n is 4. Okay, so we'll use these two formula and easily calculate it. Okay, so now we are using it. So energy, total energy is going to be half kT, half kT plus half kT plus 2 will get cancelled. Okay, so this is going to be lambda, and this integration, okay, this integration is 0 to infinity x to the power 4 into e to the power minus beta alpha x to the power 4, right? So we'll use this formula, and this is going to be gamma, n is 4, right? Gamma n plus 1 means 4 plus 1, that is 5 by 4, 4 plus n upon n, right? 5 by 4, because n is this, right? Gamma 5 by 4 I'll write in next page. So this is going to be average of E is going to be half kT plus lambda gamma n plus 1. The n is 4 here, right? N is 4. This formula I'm using. Okay. So this is going to be gamma n plus 4 means 4 plus 1 upon 4 gamma n plus 1 upon n, that is 4, this one, n into alpha to the power n plus 1 upon n. Okay, so alpha is, what is alpha here? That is beta lambda, right? So this is beta lambda to the power n plus 1, that is 4 plus 1 upon 4 upon, this is going to be e to the power minus beta alpha x to the power 4, right? We'll use this formula, x to the power n alpha x to the power n, right? So this is going to be gamma n plus 1 by 4, n plus 1 by n, right? So this is going to be gamma 4 plus 1 upon 4, okay, uh, upon alpha to the power 1 by n, right? So this one, alpha to the power 1 by n. So this is going to be alpha beta lambda to the power 1 by n, that is 4. This will get cancelled, okay, and so E is going to be 1 upon kt plus lambda by 4, this 4, right? And this is going to be, this is beta lambda to the power 1 by 4, and this will go up, right? Minus this is 5 by 4, 5 by 4, okay. So then energy is going to be total energy half kt, and this is going to be plus lambda by 4 into, if we calculate, it is going to be beta lambda to the power minus 1, okay, because if we solve it, so it is going to be minus 4 upon 4 minus 1, and minus 1 means that is 1 upon beta lambda, right? Next, 1 upon beta lambda. So this is going to be total energy. This is 1 by kt 1 by kt plus lambda by 4 into this one, beta lambda. So lambda will be remain as it is, and beta value we know, right? Beta is 1 upon kt, so we'll write 1 upon kt. 1 upon kt means kt will go up, right? So this is going to be lambda into beta is 1 upon kt, that is kt, right? Lambda will get cancelled, so this is going to be 1 by 2 kt plus kt by 4, right? So if we solve it, so this is going to be 3 by 4 kt, right? 3 by 4 kt. Okay. Now this is the total average energy for one harmonic oscillator, right? For n harmonic oscillator, because there are n classical harmonic oscillator, right? So this is going to be 3 by 4 n kt, 3 by 4 n kt, right? Now what question is asking? Question is asking specific heat we need to find out, okay? Specific heat of collection of an independent such particle, right? And which we know specific heat is, we know the formula for specific heat, right guys? This is specific heat, Cv is del upon del T, del upon del T average energy, right? The total energy. This we know, right? Very good formula. Write it. I'm writing in red. Okay. So Cv is del upon del T energy, right? Average energy is total energy. Yes. So then CV is going to be, differentiate it with respect to K. So this is going to be 3 by 4 Nk. Okay, 3 by 4 Nk, and this is the answer. So which option is matching, guys? Let me just check which option is matching. 3 by 4 Nk, that is option B is matching, guys. Option B is the correct one. Okay, option B is the correct one. Option B, right? Very good question, guys. So you need to know there are two formulas. You need to note down and memorize, guys. These are two formula. Okay, so you can easily calculate these big integration easily, right? So this is 0 to infinite integration, 0 to infinite x to the power n maybe an integer. Okay, and e to the power positive integer. So e to the power minus alpha x to the power n dx, right? So this is going to be gamma n plus 1 upon n alpha to the power n plus 1 upon n, or this is just e to the power alpha x to the power n dx is going to be gamma n plus 1 upon n upon alpha to the power 1 upon n. Okay, using these formula, we have easily solved these big integration, and we've got the specific heat for n classical non-linear harmonic oscillator. Okay, next question, question number 2. Question number 2 is, this is also easy question and good question. Okay, in an experiment, in an experiment, in an experiment, to measure the acceleration, to measure the acceleration, to measure the acceleration due to gravity, due to gravity G, that is G. Okay, using simple pendulum, using a simple pendulum, using a simple pendulum, the length and the length the length and the length and time period, the length and time period of the pendulum, of the pendulum of the pendulum are measured, are measured to three significant figures, to three significant figure, to three significant figure. The mean value of, okay, the mean value of G, mean value of G, and the uncertainty delta G, and the uncertainty, the uncertainty delta G, delta G of the measurements, of the measurements, of the measurements are then estimated are then estimated are then estimated using a calculator using a calculator from a large number of from a large number of measurements and and found to be 9.82 9.82 147 meter per second square and 0.02357 meter per second square respectively which of the following is the most accurate which of the following is most accurate most accurate way of presenting the experimentally determined the experimentally determined value of G. Experimentally determined value of G. Okay. Options are number A 9.82 plus minus 0.02 meter per second square. Option B is 9.8215 plus minus 0.02 meter per second square. Option C is 9.82 174 plus minus 0.023 57 meter per second square, and option D is 9.82 plus minus 0.0235 meter per second square. Okay, very good question. Okay, and simple question. Okay, I'll read it for you. So in an experiment to measure the acceleration due to gravity, that is G, Using a simple pendulum, the length and time period of the pendulum are measured to three significant figures. Okay, length and uh, time period of the pendulum are measured to three significant figures. Okay, so we have measured that in till three significant figures. The mean value of uh, G and the uncertainty delta G of the measurement are then estimated using the calculator from the large number of measurement and found to be this 9.8247 this meter per second square and this respectively. Which of the following is most accurate way of presenting the experimentally determined value of G? Okay, this we need to find out. Okay, so I will explain it to you. G, okay, this is the end. Okay, so since mean value of G, that is G is given, mean value of G is given uh, 9.9.82 147 okay, meter per second square, right? This is the one is given, that is mean value of G is given, and delta G, that is uncertainty, is given point 0.0235 point 0235 point 02357 02357 meter per second square, okay, so this is given. So now that we know, right, G equal to root Lg, right, 2 pi Lg of simple pendulum. So we can see G is given, right? G is given, and we know that G is 2 pi root L upon G. Ln G are measured till three significant figure, which is given, right? So it means the mean value of G we will take till three significant figure only. Okay, so we know that this is significant figures, right? We have already studied in class 11, right? So value of G we are going to take, that is three significant figure, means only three values, right? So this is going to be 9.82. Now what is it is asking? It is asking, question is asking the best way, or which of the following is the most accurate way of presenting the experimentally determined value of G. So most accurate way is going to be that G we will take it in three significant figures, right? And the delta G, that uncertainty in delta G we will write as it is. Okay, so it means the uh, most accurate way of presenting the experimentally determined value of G is going to be 9.82, that is mean value of G, right? 9.82 will take at three significant figures only, and then plus minus we will write delta G as it is, right? So 0.02357. Okay, so this is 0.02357, that is, yeah. So this is the answer, guys. And which option is matching? Option D is matching. Okay, so 9.82 plus minus uh, 0.02357. Okay, 0.02357. 0.02357. Okay, so this is the answer, guys. This is 2, guys. Okay, this is 2. This is 2. Okay, well, very good question. Next question. Very simple, actually. Next question. Third question. Okay, this is also a very good question. It is question from electronics. Okay, so question is, question number third. an AC signal, an AC signal, an AC signal of the type of the of the type of the type as shown in the figure, 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 as shown in the figure is applied across a register, across a register, across a register R equal to 1 ohm, 1 ohm. Okay, so an AC signal of the type as shown in the figure is applied across a register. Okay, so I'll make a figure first. Okay, so the figure is going to be, okay, so I'm going to draw the figure first. Okay, so this is the figure is given, right? This is -2, this is 3, and this is 8. Okay, and these are in volts. Okay, V, this is in volts, V, volts, this here between is 0. Okay, and this is AC signal is given, right? Maximum value, just wait. Okay, so this is like this. Okay, AC signal. Okay, like this, consider like this. Okay, so these are the graph AC signal. Okay, some figure is not exactly same, but yeah, this is the AC signal which is given. Okay, and this is V and this is time t. Okay, graph is between V and V versus t. Okay, so this is given. Now the power dissipated, power dissipated, need to find out power the power dissipated dissipated dissipate power dissipated across the register across across the register across the is register is okay. Options are 12.5 watt. Option B is 9 watt. Option C is option option C is 25 watt, and option D is 21.5 watt. Okay, so this is the question. I'll show you the AC signal of the type as shown in the figure. This is AC signal which is given. This is the maximum value. So this we can see the maximum value is 5. Here also 5, right? That is why minus 5, 5. Okay. Is applied across the resistor R equal to 1 ohm. Okay. And now what we need to find, the power dissipated across the resistor. Power dissipated across the resistor, which you need to find out. Okay. So how we are going to solve it? So first we'll find the peak value. Okay, peak value of voltage. Okay, peak value, that is Vm, is 5 volt. 5 volt. Okay, from question we can see it is 5 volt here, right? This is 3 volt, this is 8 volt, and this is from here, this is maximum 5 volt. Okay, so this is 5 volt is given. Now we know the peak voltage, right? So we can easily find out Vrms value. Vrms value we know. Peak voltage, that is Vm upon root 2. Okay, so now Vm upon root 2, right? So this is going to be 5 upon root 2. Now we'll find out power dissipated. Okay, power dissipated, that is power dissipated by AC. Okay, AC current. Okay, so this is going to be Vrms square upon R. This we know, right? This is the formula for power dissipated. Okay, power dissipated. Okay, so this is the formula you need to note down, and this is going to be equal to Vrms value is this, right? 5 upon root 2 whole square upon R is 1 given, right, in the question. So this is going to be 5 5 25 2 2 root 2 2 into 1. Okay, so this is going to be 12.5 watt. Okay, 12.5 watt. But this is not the answer, guys. Okay, we need to find total power. Okay, for total power, that we also need to find PDC, power dissipated by DC current. Okay, so this is going to be this we know, this for power dissipated by DC current is going to be V square upon R, and V is also given in the figure. This is 3 volt. Okay, V is given 3 volt in the figure. Okay, V is given 3 volt. Okay, so it is going to be 3 square, that is 9 upon 1, right? This is 9. It means total power dissipated total power dissipated is going to be PAC plus PDC, right? Power dissipated due to AC current and DC current, right? And that is going to be 12.5 plus 9, and this is going to be 21.5 watt. Okay, right? So this is the answer, guys. So if you get this type of question, you need to first calculate PAC and then PDC. Then you need to get total power dissipated, and that would be your answer. Okay. Okay. So 12 point. Sorry, 21.5. Which option is matching? Let me check which option is matching. Option D is matching. Okay. So this is the correct answer. I hope you understood, guys. Okay. Okay. Next question. This is an electronic question. Okay. It's a very good question. Question is question number 4. An NPN transistor and NPN transistor NPN transistor is connected NPN transistor is connected in a voltage divider in a voltage divider in a voltage divider configuration. Okay, an NPN transistor is connected in a voltage uh, divider configuration as shown in the figure. As shown in the figure below. Okay, so I'll make a figure. I'll make a figure here in next page. Okay, so this is NPN transistor. Okay, this is like this, and this is going to be, this is grounded. Like this. This is B. This is emitter. This is collector, and this is going to be like this. This is 20 volt. This is RC. The value is 5 kilo ohm. 5 kilo ohm. This is collector, and this value is 1 kilo ohm. 1 kilo ohm. Beta is given 50, and this is R1. R1, the value is 80 kilo ohm, and this is R2, the value is 20 kilo ohm. 20 kilo ohm. 80 kilo ohm, okay, and this is 5 kilo ohm. Yes, this is the figure which is given, okay. And question is, if register if register R2 disconnected, I'm writing here, okay, if register R2 is disconnected, the voltage VB, the voltage VB at the base, at the base and VC at the collector, at the collector changes as follows, changes as follows, okay. Options are option A, both both VB and VC, V and VC increases, okay, increases. Option B is both VB and VC decreases, okay. Option C is VB decreases but VC increases, and option D is VB increases but VC decreases, okay. So we need to find which option is the correct one, okay. So question is this, question is NPN transistor is connected in a voltage divider configuration as shown in the figure, okay. So this is the figure, this is the NPN transistor which is connected in the voltage divider configuration, okay. These are the values which is given. If resistor R2, if the resistor R2, this one is disconnected, the voltage VB at the base, this voltage, okay, and VC, that is collector voltage, VC at the collector changes as follows. So which option is correct, okay, like both VB and VC increases, decreases, or one increases, one decreases, okay. So these are the options. I'll solve it now. Okay, so here first we'll found here VB, okay, value of VB. So voltage divider rule here, right? What is going to be VB? VCC R2 upon R1 plus R2, okay. This one VCC, VB we are finding this voltage divider rule, okay. So VCC Okay, so this is R2, and or we can write it as VCC upon R1 upon R2 plus 1, right? We have divided by R, numerator and denominator. Okay, so this R1 upon R2, right? What this implies? This implies if R2 increases, if we increase the R2, right? Because increasing value will increase, right? If R2 increases, it means VB also increases. Okay, since also we know VBE equal to V minus VE, right? This VB equal to VB minus VE. This implies VB is going to be, sorry, VE is going to be, VE is going to be, VE is going to be VB minus VB, right? And also IE, we know IE equal to VE upon RE, emitter current, emitter voltage upon emitter resistance, right? Emitter current we are talking about RE, and we know this IE, emitter current, is almost equal to IC. Okay, IC, and all so we can see as VB increases, VE also increases, right? How? This is VB, VA, right? If VB increases, this VB. If VB will increase, then VE will also increase, right? From this formula. Okay, and thus we can say if IE increases, because I equal to V upon E, V is increasing, right? V increases, I increases. So if I increases, I increases, right? I equal to IC, right? The I and IC are almost equal, right? So I increases means IC also increases, right? Since here also we know VCC equal to VCC minus ICRC, right? So here you can see if IC increases, this we know. If IC increases, it means this IC will increase, then VCC decrease, right? Then VC decreases, right? So it means from here we can conclude that VB increases, right? If we disconnect the R, right? VB increases, okay? VB increases and VC decreases because IC decreases by this formula, okay? So which option is matching? Option D. VB increases and VC decreases, right? So this is the answer. Very good question. Okay. Next question, question number 5. Question number 5. Okay. I hope I'm audible. Let me just check. VB. Yes, I'm audible. Okay. Next question. Now, guys, part C questions started. Okay, this is the first question of part C of June 2019 CSIR net physics PYQ paper. Okay, physics paper. So this is the first question of part C. Now, because so now part B questions completed of CSIR net physical science June 2019. Okay, so now I am starting part C questions of CSIR net physics June 2019 paper. Okay, So first question of part C, that is question number 5 is, this is the question from digital electronics from logical gates. Okay, question is, why denote the output, why denote the output in the following in the following in the following logical circuit, in the following logical circuit. Okay, logical circuit is given. Given. Okay, this is the figure is given. If y, the output is given, a ab plus c bar d bar, the gates G1 and G2 must respectively be okay. Options are, very good question, and it is asked in part C, 5 number question. Okay, uh, or and NAND. Okay, option B is NOR and or. Option C is and and NAND. Option D is NAND and or. Okay, so the question is, why denote the output in the following logical circuit? So this is the logical circuit, and y and y is denoting the output, and this value is given, that is y equal to ab plus c bar d bar. Okay, and the gates G1 G2 must be respectively. So what are the gates G1 G2? So that it will give value y equal to AB plus C bar D bar. Okay, that is the one. And options are given, that is OR gate, NAND gate, NOR gate, right? This. So we'll check one by one, right? So OR and NAND, it is not going to be. We'll check with this NOR gate and OR gate. Okay. So here you can check here, like this is OR gate. This is A and B. Okay, A and B. So we can say, if we go here, it is going to be A bar and this is going to be B bar, right? Here, if we take that option B, that is NOR gate, right? So NOR gate, we know what NOR gate do. NOR gate does is, that is A bar plus B bar. Okay, it will become A bar plus B bar, right? Because we know the NOR gate, right? NOR gate means if AB is given, A plus B bar, right? That is the NOR gate. OR means A plus B. Will add, NOR means will add, and then there would be conjugate, right? There would be bar, right? So this is going to be, we know how to solve this. We know the De Morgan theorem, right? De Morgan theorem, if you want to remove the bar, so we will remove the bar. If you want to break the bar, we will break the bar, and the sign will get changed. If it is plus, it will be multiplication, right? And if it is multiplication, dot will changes to product, plus, and plus will changes to dot, right? So it is going to be, so there we are breaking the bar. Okay, so this is going to be A bar. We have taken it NOR. Okay, you can check one by one everyone. So I'm checking by B. So this is going to be uh, A bar bar, right? Dot B bar bar, right? And we know bar bar is, A bar is by De Morgan theorem. A bar is going to be A, right? So this is going to be AB, right? So AB is coming here, right? And this is NOR gate, and second we say it's a OR gate. Okay, option according to B option. Okay, it's OR gate. So now here we'll check. So this is CD, right? This is a NOR gate. NOR gate means this is going to be C plus D bar, right? And we have put this is a NOR gate and this is OR gate. Okay, so OR gate means what will do? This is going to be AB value, right? AB plus C plus D bar, because this is OR gate, right? So we have, this is NOR gate. So if we solve this by NOR gate, this is giving AB, right? And we are saying it is OR gate. So this is C plus D. So OR gate means this value and this value both will get added, right? Or now, but output is this. So what we'll do is now we'll simplify this further. Okay, AB plus, right? So this is going to be, so what we are going to do, AB plus will break the bar. Okay, so we know how to break it. For breaking the bar, will break the bar and the sign will change, right? So this is plus, this is going to be dot, right? In multiplication, addition going to be into multiplication. So this is going to be C bar D bar, this multiplication, right? So this is giving the correct answer. Means if we consider this as a NOR gate and this as a OR gate, this is going to give this uh, output Y, right? Same output, AB plus C bar D bar. It means option B is the correct option. Okay, option B is the correct option. You can also put OR gate and NAND gate in these gates, and you will find incorrect answer. Okay, so correct will be, if we and the correct will be option B, right? Option B. So we know what is the sign and how OR gate, NAND gate works, right? So this is the correct answer, option B. Okay, so this is the output. For getting this output, this gate must be NOR gate and this gate must be OR gate. Okay, well guys, time is over, so I'm going to stop here, and thank you so much for watching my lecture. And I also would request the people who haven't subscribed my channel yet, please subscribe my channel and watch my lectures, and my lectures are going to help you to crack exams related to physical science. Okay guys, thank you, bye now.